Welcome. This next set of lectures is all about descriptive statistics. So we're going to plunge right in here really quickly. But if you're the type of person who historically your eyes kind of glaze over at the thoughts of statistics, just keep in mind that all we're doing is using numbers to describe what's happening and really just to tell a story about the data. I'm going to take you through this very slowly. Those of you who've had stats classes recently, a lot of this will be review, but I hope that maybe it gives you a little bit different perspective on a couple of concepts you may have wondered about. Keep in mind too that we use descriptive statistics all throughout our lives. If you're following politics, you're going to be inundated with polls and predictions, and all of that are based on the statistics that they use to describe and to tell stories. If you're a sports nut, statistics are huge in that, and we look at a lot of different features of teams and different things like that through a statistical lens. So as we move through this first lecture, what I would like you to get out of this is a good idea of what I mean by descriptive statistics. And basically there are three concepts. We're going to talk about central tendency. In other words, how we describe the data as a group and the tendencies that are in there. Then I'm going to talk about variability, which is how different the scores are from each other, or the numbers are from each other. And last of all, in the last lecture, I'm going to talk about relationships and start to see how statistics, different data sets go together. And I'm going to talk you through a lot of different graphs as we represent information. We tend to like to be able to see something quickly and easily, and that's what a graph does for us, obviously. So it's important that you can interpret them. First of all, a bit of vocabulary. When we're working with statistics and numbers to describe things that we see in the data, we have to keep a distinction between whether we're talking about the population. Remember, that's all the people who could possibly belong to this group, and the sample, and that's what we actually pull the data from. So when we're talking about a population, we use the word parameter, and that is the measure of a characteristic of the entire population. So some common parameters would be the average income of all CCSD teachers, and that would be a parameter statistic, but we usually just call it a parameter. We represent it with what's called a mu, mu. It's a Greek symbol, and it's that funny little U looking thing. So we could say that the average, or the mu, for the mean that we're doing is 43.7. And we use a capital N when we're representing what we think is in the total population. Now let's compare that to a statistic. With a statistic, think sample. You're never going to have a statistic on the entire population, because statistic is always equated just with the sample. So it's a measure of the characteristic of the sample. So we could say the average income of our CCSD sample of teachers is, and we represent that with an X. So X equal, comparing it to the parameter above, we could say that the mean is equal to 43.7 of some measure that we're using. So the sample mean is 43.7. And we use a lowercase n to represent the number in the sample. So if you want to see how many people or groups the data was collected on, then you're looking for that smaller n. Before I go into scales and how we kind of use numbers to tell the stories, I want you to think back to some basics about numbers. And you know this intuitively, but you may not ever have thought about it. we're using numbers to represent some aspect of behavior or knowledge, but knowledge isn't a number. We're using the number to represent something. So we say things like she's in grade 7, or his IQ is 103. She scored 17 out of 30 on the semester exam. Or we use numbers to code categories. So my last example on this screen here is we're using 0 to represent no college. 1 we're using to represent 2 years of college. We're coding the data, you see, with a number instead of using the words. 2 represents a college degree, 3 represents postgraduate coursework, and 4 equals a graduate degree. So what I've done is I've taken an arbitrary set of numbers to represent the story that I want to tell. And this helps because computers like to work with numbers a lot better than they like to work with words. So I've coded the data. And we can do that because of some characteristics of numbers. So when we're working with statistics, remember, we're looking at a sample, we're applying numbers to behaviors, and all we're doing is describing the state of that sample, describing what is. So we're saying the average score or the correlation between height and weight is. All we've done is summarize into indices these descriptions that we want about the data. Now, there's the next level of statistics is called inferential statistics, and this is when we make generalizations, or we make inferences from the sample data to the population, and we start to analyze and make predictions, or we could say things like, based on the data from the sample, we predict that 7-year-olds will read 8 books this year, or based on so-and-so's batting average, we would suggest that he bat in this order in the batting lineup. We could say the intervention was successful. There was a statistically significant difference between group 1 and the control group. And then we give the actual statistics that were run there, the results of the inferential statistics, comparing those two groups. As soon as we start to do that, we're moving into the realm of inferential statistics, which is not where we're going to go at all in this lecture. So when we're just describing, when we're just using numbers to describe, we have procedures and short little analyses that we can run. Most of them are arithmetic. We don't even get into anything complicated with this. And what we're doing is we're putting those numbers into indices or descriptors for the data set. So there are 3 that are really important. First of all, we're going to look at the central tendency. And the simplest question for that is, what's a typical score in this data set? Well, obviously, what do we mean by typical? And I'm going to get into that in a minute. Variability. There, in that one, we're looking at how similar or different the scores are on the data set. Did all the kids score about the same on that exam, or was it really spread across a range? That's what we're talking about with variability. And then relationships. Are the scores from 2 different data sets related? Is there some kind of pattern that we're seeing here where when one changes, we can see that the other pretty well changes too? Now, going back to numbers, these are the characteristics of numbers that you've probably never even put into words, but you know them instinctively. Numbers are distinct. So when I say 3, your brain knows that that is not the same as 10. It is distinctly different, and you can have this concept of a 3 being different than a 10. But at the same time, numbers are relative. In other words, our brains process numbers as we can rank them. So we know that 3 is smaller than 10. Numbers relate to units. So we give every unit a number, and we take it down to decimal points even. But your brain knows that 3 is 7 units less than 10. You have this numbers work this way and you understand that there's a difference between 3 and 10 of 7 units. And then the last piece that's really important is that numbers relate to proportionality. So you know that 3 is four times smaller than 12. You'd have to have chunks of 3 to get to 12. And over the years of math classes from kindergarten on, you've actually learned these properties of numbers, and there are more, but these 4 really apply to the way that we describe things. What we do when we're describing things is we have to decide, first of all, what kind of scale we are using to describe something. So we know that numbers are distinct. 3 is not the same as a 10. That means that we can have a nominal, think naming, or categorical grouping scale. And that simply means that we are using them as I did before. 0 represents no college. 1 represents the group of people that have up to 2 years of college. And all I'm doing is taking a number and applying it to a category. And it could honestly be any number. I could use 4,328 to represent my no college group. It's not the amount that we think of in numbers that matters with naming. We're just simply using it as a code, much like we use 01, 01, 01. And we do this a lot. You'll see it very commonly with gender. You give a 0 to one group and a 1 to the other. Makes no difference which group you use. You could use 1 and 2. You could use 1,500 and 1,600. But it's just easy to deal with small numbers. All we're doing is using the number as a code for the name of the group. Now, one of the properties of numbers is that numbers are relative. They relate to each other. They rank. And so then we can use a scale that's ordinal. That means that the categories are ordered as we move along, and we can put ranks in there. But the unusual, or the piece to remember about ordinal scales is that they don't have to have equal intervals in them. If I'm looking at the placings in a race, we have a foot race, and this person comes in first, this one second, this one third, this one fourth, and so on down the rank of how they cross the finish line. I am not saying that the interval between the time when the person who was first crossed the finish line to the second person to the third person, those intervals are not necessarily the same. And in an ordinal scale, you must keep that in mind. I am simply ranking first, second, third, fourth. I'm not saying that the intervals are exactly the same. Now, when I get down to the next property of numbers, that numbers relate to units, that's where I can get my equal intervals. And we actually call that an interval scale. And it means that the numbers on the scale have a distance between them that's the same. So the distance between 1 and 2 is the same as between 2 and 3 and between 3 and 4. But there's no meaningful 0 in this. So interval scales, things like test scores. If I give a test that's worth 50 points, and I know that the interval between someone who scored 35 on the test and I know someone who scored 45, that 1 unit each time represents a point or something very equal. So the difference between 35 and 45 is the same as the difference between 25 and 35. In other words, I'm saying there's an actual value or space or size, if you want to each number on that scale. But in an interval scale, there's no meaningful 0. So think like IQ. You don't have an IQ of 0. There's brain function there all the way down. 0 doesn't mean anything in that scale. And it doesn't mean the absence of the property. So achievement tests. Zero, even if a kid scores 0 on the test, that does not mean that that child knows nothing about the subject. It means that that the person didn't get those points, and the space from 0 to 1 is the same as the space from 1 to 2, but it doesn't have a meaning that the child knows nothing. That goes down to when we get to proportionality and we're dealing with a ratio scale. In a ratio scale, that 0 means the absence of something. So if I'm measuring height, and if you can imagine there was nothing there to measure, that would actually be measuring on a ratio scale. The 0 means the absence of height or weight or time. 0 means that no time has elapsed if I'm measuring time. Here's another way to look at it with a chart. So down the left-hand side are the names of the scales, and this is a good chart to print off or flag in your notes or whatever it takes so that you can come back and refer to this. So nominal, we're talking about categories or groups. We're just using numbers to label things like gender, eye color, political party. There's not an amount that you're a Democrat or you're a Republican or you're an independent. There's not an amount to that we can actually measure. Then ordinal, remember this is when we're lining things up in an order and the intervals don't mean anything. So a military rank or you're placing in a race or your birth order. And I've really messed up on that slide. I'll fix it before I print it for your notes. And then the interval scale is where the difference between the numbers actually does have a meaning. And that's where we have things like IQ or an attitude scale or the midterm score on a test. But remember that 0 doesn't mean the absence in an interval. And then ratio, you can see there that this time 0 means something. So age, yeah, if someone hasn't been born yet, they don't have an age. Number of children in a classroom. If you said you had 0 children in a classroom, that would really means something. The 0 means something. Now, commonly when we're representing data, we use graphs. And the graphs that we're going to tackle first are about frequency. How often does this score happen? Or how often does this height happen? Or this choice on an attitude scale? And these are the 5 most common, and some of those are even more common than others. So I'm going to take you through each one of them, and this will probably be review for a lot of you. So, frequency table. If any of you have taught elementary school, you've done these a lot. My granddaughter's in kindergarten, and so they have the tooth chart. And every time a child loses a tooth, another tooth goes up in their frequency table. And then the teacher, of course, is going to slowly change that to a pictograph of some kind for the children so that they can start to see how we represent data. So looking down this, on the left-hand side are the scores from the test. And then down the right-hand side under frequency are how many times that score occurred. So there were 3 people who got 22 on this measure of whatever it is. There were 4 people who got 24, and there were 3 people who got 26. So all I've done on the right-hand side under the frequency is list out the number of occurrences. You'll often see this mostly in elementary school, not so much in anything to do with research, but some people still like it. It's called a stem and leaf plot. And it's only useful if there's a very small number of observations or scores that you're dealing with. And how this works is down the left-hand side of this T chart are the tens. So the 1 represents 10, the 2, 20, and the 3, 30. And then off under the part of the chart that relates to the ones are the different ones. So a score of 16, there was one person that got that, you'll see. So under the tens, there's a 1 and a 6. 22, you'll see that there's a 2 recorded in the tens column, and then there are 3 2s over here. So that represents 22, 22, 22, and so on. And you can see why it's called a stem and leaf graph. So there's your 16, and there's your 3 22s. Now the other way to represent the frequency of distributions is with the histogram. So all that does is put a bar to represent up the y-axis, up the left-hand side of the graph, are the frequency or the number of occurrences. And then if you look over towards the center of the graph to where the tallest bar there actually says 24, and you can see back from our frequency table that there were 4 people who scored 24. So that bar represents the spot where you can see at a glance that the most frequently occurring score was 24. And then 22, going to the left, there were 3 people scored that way, and going to the right, there were 26 and 28 points respectively. There were 3 people in each one. So you can see how we've become more sophisticated from a simple frequency table where you have to actually look at the numbers and kind of picture it in your brain, to a stem and leaf where you can see that most of the scores were in the 20s, and you can see the range there of the distribution, to a histogram where you can see at a glance how the scores group and what the frequency is. Then, if you picture these two on top of each other, you've got a frequency polygon. So imagine that instead of a bar, you put a dot at the top of each of those bars, and then you simply connect them with a line. And then you've got what's called a frequency polygon instead of a histogram. But it's still helpful because you can see at a glance where the most commonly occurring score was, and once again it's 4. Now notice in the histogram that the bars touch each other. That's a signal that those intervals mean something, that the distance from 22 to 24 is the same. It looks like on this measure there were 2 points for each question or something like that. So they're continuous. That's an indication that it is an interval scale of some kind, and they touch each other, meaning that the units actually matter. Now compare that with, this would be a frequency chart if I was simply using across the bottom there, you see I've labeled them grade, kindergarten, first, second, third, fourth. All I'm doing there is 4 for 4th grade doesn't mean anything. All it is a label. So in this case, there are spaces between the bars to show that 3rd grade is simply a label that I'm using there. So I've talked through different scales of measurement. If this was review for you, great. If it wasn't, you may want to go back and look at your notes and listen to this again, because scales that we use for measuring are incredibly important in understanding statistical descriptions.